Virgo Interferometer.
Okay, so I think it's my turn, and I share my screen. Because I will give you an introduction before your visit. My name is Piero Chessa. I'm a physicist and I work at the Super Attenuator team in this Gravitational Wave Detector, which involves now 50 people on site and many hundreds of people working on data analysis all around the world. And we will go through some theory and some about the phenomena we detect here and about the detection principle. And then I will give you some information about what we have at here as results of our measurements, our observations. So we will start with a jump to the 17th century, when Isaac Newton published his universal gravitation theory, which is a sum of bright intuitions plus a wonderful mathematical work by Newton. One of these intuitions is the idea that forces are interactions. That means bodies, couples of bodies interacting between each other. And in the case of gravitation, this interaction is proportional to the masses, the natural masses of the bodies, and inversely proportional to the square of the distance. It is very nice. A very nice theory because it explains with very nice correspondence the elliptic orbits of planets. It's one theory for different phenomena, from orbits to falling objects. So it's a dramatic leap of culture. It is so precise that we still stick on it for motion calculations in the sky. But it has also something going wrong. One of these going wrong things is the orbit of Mercury. Mercury, as you may know, is the closest planet to the Sun, that is the fastest one. And the orbit of Mercury is quite an ellipse, but the ellipse itself is turning around the Sun. And there's no classical explanation of this phenomenon, of this motion. And there is another point that has been pointed out at Newton's time, just at Newton's time, and it has to do with the shape of this interaction. You can think to a very, very far star, and when the star is there, that direction, you feel a pull in that direction. But if the star all of a sudden changes its position and goes in another position, then you immediately feel a pull in a new direction. And there's something weird on this. There's something missing in this expression, this equation. And the missing is time, because it's contrary or our experience that you can know what happens in a very, very far apart place of the universe without any delay. So there is a time question here, a time point here to be solved. The man who took the challenge to explain things is Albert Einstein, who published in 1915 his general relativity theory. And it started from some assumption. The first one is that all repetitions of the same experiment in any free-falling lab have the same results. So to think to a very far away falling lab, far away from any mass falling lab, this falling lab indeed is an inertial system. So that means that in any free-falling lab and in any inertial system, experiments must have the same results. That means they must have the same forces. That it means that they must have the same interactions. And the consequence is, if you compare the two situations, that gravitation must not be an interaction. So gravitation is not an interaction, is not a property of matter. Then it should be a property of space-time indeed. And we usually picture this idea like this. Think to a grid like here in this picture and on bottom of my page. This grid represents, I warn you, a 2D space because we have no fourth spare dimension to represent distortion of the 3D space. So think to a two-dimensional space which is flat if no mass are in it. But when a mass is in a 2D space, this 2D space gets distorted. So close to the mass, you have distortions, the higher distortion. Far from the mass, you have the smaller distortion. And this scheme of thinking is nice to think of what happens when a free body, travels through a 2D space. If the space is flat, the shortest path between 2 points is the straight line. So a free body goes straight, and the light wave goes straight as well. But if the space is distorted, then the shortest path between 2 points is no more the straight line. And so a free body goes through this space by a curved trajectory up to being enclosed in an ellipse. And for the light is the same. Light would go in this space through a curved trajectory. But what gravitational waves are? Gravitational waves are this distortion of space traveling in the space due to some conditions. They are predicted by general relativity. They are oscillation of space-time traveling at the speed of light. And they are produced if asymmetric mass distributions are oscillating, are moving with a very compact and dense distribution of mass with rotating relativistic velocities, speeds. And they so decrease from the source with an amplitude decreasing as 1 over the distance. Here in this box you have an example of what a dense body is for us. Is a black hole or a neutron star. And so this is the you see the moving picture here is a cross section of the effect of a gravitational wave. Gravitational wave in this case is traveling perpendicular to the screen, coming out of the screen here, and on the screen you have perpendicular effects. That means that when the horizontal length is decreased, the vertical one is at the same moment increased. So you can imagine to make differential measures of a gravitational wave by measuring perpendicular variations of a length. But what kind of an effect do we expect? What intensity of these waves do we measure? A measure of the intensity is usually the fraction between the variation of a length and the length itself. So it's a dimensionless quantity. And for the far astronomical events we measure here, this amplitude is such like 10 to minus 21. That means that in our interferometer, where we have lengths of 3 kilometers, this length of 3 kilometers, when the gravitational wave comes, change the length by 3 times 10 to minus 18 meters. And if you want to know what 3 times 10 to minus 18 meters mean, you have to take an atom, to break the atom, take an electron from within the atom, measure the diameter of the electron, and that's more or less the measure of 10 to minus 18 meter. I want to be even more dramatic, and I give you one more allegory. Think to the surface of the oceans, all summed up. The area is this figure I wrote here on top right. Then you think you are in a boat on the ocean with a can of Coke, and here is the volume of a can of Coke. Then you pour the liquid on the ocean, and you measure the level increase of the ocean. And what you measure is exactly 10 to minus 18 meters. So we are trying to measure the level increase of an ocean due to not 1, but 3 cans of Coke. I told you this because there are 2 things that must be very clear when we think to this kind of measurements. That these 2 things that are very important are, first, we have to be very, very, very accurate and sensitive when we make these measurements. But the second, which is important as well, is that this ocean must be flat. We have to take out any disturbance, any noise from this ocean. So we have to do things to be very sensitive and be very, very quiet. Something about the detection principle. When a gravitational wave impinges on your detector, you can't measure the length variation by a meter, because the meter length changes with the wave, with the space itself. So you need a good idea. And the good idea is light, because light has a constant speed, even when a gravitational wave arrives. So you can send a light wave to a point, to the end mirror, taking it back, measuring the travel time, and you have a measurement of the length between you and the mirror that reflected the light. And that's the principle of working of the Michelson interferometer, which is the main frame of our detector. We didn't invent the Michelson interferometer. Michelson interferometer has a glorious history in physics, but it is perfect for this kind of measurements. It works like this, A wave comes out of a laser source, goes through into a beam splitter. This beam splitter splits the beam in 2 parts and sends the 2 parts in perpendicular directions. So one part of the wave goes to direction to an end mirror, the other part goes in the perpendicular direction to another end mirror. Then the reflected waves go back to the beam splitter. One goes through the beam splitter, the other is reflected by the beam splitter, and both go to the light detector. And here, something very interesting happens. If the 2 arms of the detector have exactly the same length, then the 2 overlapping beams have exactly phase opposition. That means that when one is at the minimum, the other is at its maximum. When one is at 0, the other is at 0 as well. So the sum of the 2 is a flat line, a flat signal. So no light on detector if the 2 branches of the interferometer are exactly the same length. But if a small difference of length happens in the 2 branches of the interferometer, a different change of a different phase is present in the two beams going to the detector. And so the sum of the two is no more a flat line, is a wave itself. So you have no light when there is no disturbance, no wave, and you have a light on the detector when a gravitational wave comes to the detector and changes differently in the differential way wave the length of the two arms of the detector. There are many other things I could tell you about the detector. We had made many other upgrades of the detector, but I will leave this for questions if you have, because I want to give you some information about the attenuation part of the detector. So remember, we have to measure 10 to minus 18 meters variation of a length over 3 kilometers. So any fluctuations of Earth air temperature along the arm of the interferometer are dramatically limiting our measurements. For instance, think that now, this moment, we have oscillations due to seismic vibrations with amplitude like 4 times 10 to minus 8 meters. That means that we have to have mirrors hanging to roofs where the roof is moving, and the mirrors must be more than 10 to 10 times steadier than the roof itself. So when we transmit, then we hang these mirrors, we have to make a dramatic, a huge attenuation of non-stations. Attenuation in one step, a huge effort in one step, then you make more smaller efforts to be ready at the end of the chain, and that's what we do in our detector. Here you have a sketch of the towers, of the attenuation towers. Here at the top, at the bottom of the chain, you have, at this point here, the mirror. In this drawing, this mirror is the beam splitter of the detector. Over the beam splitter, you see a chain of filters, of attenuators. Each of these filters, which are indeed oscillators, make an attenuation by a factor 100. We have 6 of these filters, so we have 6 times 100 time attenuations. That means we have 10 to 12 factor of attenuation at the end of the chain. So we succeed in making the attenuations I told you before. But that's not the only problem. We have pressure fluctuations to be controlled in a very, very big vacuum system with very low frequency pressures. We have fluctuations of laser light to be controlled. We have mirror quality to be controlled. We have teams for any of these topic going on, increasing the sense, increasing the quality of the device. So what do we do with this device, with this huge device? At the beginning, up to 2015, this was an experiment, and the purpose of the experiment was, first of all, to show that that gravitational waves exist and can be detected. This task has been solved, has done in a few years ago, and from that moment on, we do not need to show that the gravitational wave exists, because we have gravitational waves continuously, and we may use them to measure activity in the sky, in the faraway sky. So it's now we have a detector for quite peculiar astrophysical phenomena. These are small, a short list of them. First of all, coalescence of binaries, of compact binaries. That means couples of black holes of neutron stars, or couples of a couple made of a neutron star and a black hole, coalescing. That means going in a collision. And these have been observed today, and in principle we can see emission of gravitational waves by rotating neutron stars or supernova. And this I show you now is the first historical document of the first detection of the gravitational wave in 2015. These diagrams here are the experimental results by two gravitational wave interferometers in the United States, the two LIGO, Hanford and Livingston LIGO laboratories in the United States. We have no Virgo signal at this moment because Virgo was down for an upgrade at this moment. But you can see, you can compare their experimental results with the theoretical forecast for this kind of event, a binary black hole coalescing in a place up down in the sky with some hundreds of megaparsec from us. This kind of event has been recorded many times. Here we have, here you have another event like this one. Here again we have another with this one in 2017 has been detected by Virgo as well, together with the LIGO and with the two LIGOs. We work in collaboration with the American laboratories. And this is the short explanation of the typical shape of these signals. They have a starting part where frequency and amplitude are increased slowly. It's the moment when the two bodies rotating one around the other, rotating to each other, go closer. And then they coalesce, and in this moment here you have the dramatic increase of frequency and intensity. Then they become one body, one single body. They release a lot of energy, but this is done in a longer time, and this is the relaxation part of the signal. So slowly increasing frequency and intensity, a peak, a chirp at the moment, and then a relaxation. And this here is the first detection of a binary neutron star. It comes from observation of LIGO and Virgo as well together. You can maybe notice that the signal from Virgo is weaker than two other, and and the signal in Hanford is weaker than the signal in Livingston. The differences are not due to the sensitivity of the detectors. They are due to the geometry of the emissions, to the fact that the detectors are placed on the Earth in different positions and with different orientations. And that gives us information to the position of the source. So from the comparison of the intensities of the signals, we could point out the point in the sky where we thought the source was, and we give this alert to other astronomers, and other astronomers made their observation in the electromagnetic spectrum, and they took other information about the event. So we have the first example of a multi-messenger observation of an astronomical event, and it was an historical event in the story of astronomy, because we took a lot of information about events, even about mysterious effects like gamma ray bursts in the sky. So as you see, we need to have more than three, at least three interferometer, gravitational wave interferometer on the Earth to be precise in observations. We have three now, which are the two LIGO and Virgo. We have a smaller one in Germany with a smaller sensitivity, but we'll have soon a fourth important big detector in Japan, which is called Kagra, and we are designing and starting building another detector in India called LIGO India. So here you see a list, a part of a list of the events that Virgo detected during the last observation period, which has been closed at the beginning of the lockdown in last year. And if we count them, we see that we have more than one detection per week. That means that, as I told you, that the first part of the history of Virgo, the experimental part, when we call it an experiment, when we wanted to show that gravitational wave exists, is over. Now this is an astrophysical device for observations of sky. And so this will contribute to the observations in astronomy and for a to be continued history of astronomy. And that's all, I think, on my part. And I think I hope you enjoyed the visit and you follow now my colleague, Valerio Boschi, that will lead you in this visit.
Dear all, so thank you, Piero. Valerio, are you there? Okay, before we switch to the main room, just a second. We have a little poll, just if you could please answer to a question should have popped up, I suppose. Okay, good. I see people replying. We just wait for 1 minute until everybody or those who want have completed the poll. Okay, I think nobody else is going to vote. Thank you, everyone. So I close this now. And we switch to, just a second, I'm sorry, what is this? And we switch to Valerio. Valerio, whenever you want.
Okay, I don't know, can you see me and hear me well? Julia, can you hear me?
Yes, Valerio, you're fine.
Okay, no, I was just verifying. Okay, no, yeah, we are here in an area, in a building that essentially contains offices, just offices, and an exposition area. Then we'll move to the detector itself. And this is just, as I said, an exposition area in which we have some items that are interesting to see before seeing the inside of the detector. And the first one is this model of interferometer. This is a Michelson interferometer. You have probably heard about it, of course, in the slides you just heard, but also before, due to the Michelson and Morley experiment. Now, there is a very famous experiment in the history of physics. The experiment that actually prove the fact that the electromagnetic waves can propagate in vacuum. The fact that essentially ether, or what is middle of propagation, what was thought as a middle of propagation of electromagnetic waves was not indeed existing, was not present. Is not present in the universe. So light can propagate actually in vacuum, something that was not acceptable for the physics of the 19th century. And the scheme remained the same. I mean, the Michelson scheme is the same of the Michelson experiment in this model, but the optical scheme of Virgo is slightly more complex. It's actually much more complex. But in any case, the basic components remain the same. So there are much more components, but the basic one are the same. And the main component is the laser. That is, in this case, red laser of infrared one. And you see here, this is just a red laser, like the one that we use for the slides, not for the presentation. But for Virgo is instead the infrared laser. It's 1 micron of a wave. This laser light propagate through a semi-reflective mirror that divides the beam in two. 50% goes through the splitter and goes straight. So just goes straight. And that is reflected by a reflective mirror, completely reflective mirror. And so the beam goes back and goes back to the B splitter. So the B splitter is half mirror, half lens. So half transmits and half reflects and anti-reflects. And so 50% is reflected at 90 degrees and goes through the other arm, and then is reflected again on another mirror. And so both beams reaches the B splitter. Then after they reach the B splitter, they passes through, here in this case, through a lens that then focalize on a plane that here is simply, you see a piece of plastic. But what you see are the interference fringes. The interference fringes that, as you can see, are constantly moving due to the movement, due to the, for example, the voice, my voice actually, and the fact that we are moving close to the instrument. So the nice thing is that this object, even though it's very small, is extremely sensitive. So, for example, if I very slightly touch the surface of it, that is actually very heavy and stiff, the interference fringes moves by a lot. And from the movement of the interference fringe, one can measure the difference in length of the two arms. So this is essentially the main goal, I mean, the main use of the interferometer is to make measurements. It's like with a ruler, no? When you have a ruler and you want to measure a length. The difference in this case is that the measurement is not a direct measurement, is not a single instrument. So a direct measurement is a differential measurement. It means that one can measure the difference of the length of one arm minus the length of the other arm. That's the differential measurement. And the other important difference is that with the ruler, you measure the distance in DC. So that means that you measure the distance at zero frequency. In our case, it's different because we measure the distance, the relative distance, the relative length of the two arms in a very specific band, in a band that in frequency that is actually very close to the bandwidth of the human ear. So it's from 10 Hertz to 10 kilohertz. So we make with this measurement not at zero frequency like we make with a ruler, but starting from 10 Hertz until 10 kilohertz. So that's a very important difference because that's the reason why also we can reach extremely high level of sensitivity. In any case, even this instrument is very small, still very sensitive, as you have seen. Okay, here in front of that, there is this sort of tissue that essentially we use to show the effect of curvature on gravity and so on. This is a metaphor, of course. Some theorists also think that this metaphor is not completely correct, but in any case, this is give a rough idea of what space-time is. And the idea is that if you have a mass in a point in the universe, this mass changes the curvature of space-time. It actually changes both. So it changes the curvature of space-time and changes also the time. So when there is a mass, the time goes slower respect to the point in a universe in which there is no mass, in a point that is completely empty. And in that point, the curvature is not zero, so the space-time is not flat, it becomes curved. So it's like, when you put a rock, this is simply a rock, you put on this tissue, you got the tissue curved due to the presence of the rock. The idea is that gravity is simply the effect of this deformation. So if you don't make force on a very light object, much lighter than the rock, if you simply let it go, it goes towards the object that has deformed the space-time. And this is gravity. So there is a natural attraction due to the fact that the structure is curved. Of course, in this case, there is also gravity, that was like this. But even if you imagine to don't have it, still, since the object moves in this structure, is constrained to move inside of this curved structure, in any case, we'll have a trajectory, a natural trajectory that tends toward the object that is deformed the space-time. So it will not have a straight trajectory, but a curved one. If you have an initial velocity, you have something like an orbit, like a planet, and or the moon around the Earth. So essentially, all the gravitational phenomena can be explained. The Newtonian mechanics can explain using the curvature of space-time. And this is actually the true version of gravity, not the Newtonian one, but the relativistic one is the correct version, is actually the most precise. Of course, the word correct is not good in physics. No, it's not the right word in physics. You just got the test theory at this moment. This does not mean that is the definitive one. In any case, the most precise one. And so from this metaphor, from this object here, is more clear what gravitational waves are. Gravitational waves are ripples of this structure, and they are made just by deforming it. So it means that if you, for example, remove this rock, you induce a vibration. That's the same if you put the rock on it. This vibration are gravitational waves. So if you imagine, for example, this rock is a supernova, is a big star, it explodes. It's like starting from a curved space-time, and the space-time becomes flat because this object has exploded. So this means that the mass has been spread in a very huge area. So it's like removing it. But removing it, you induce an oscillation of this fabric. And those are exactly gravitational waves. So just oscillation, ripples in the fabric of space-time that propagates at the speed of light, and then they reach our detector. And so this means that they move the optical components, in particular, they move the terminal mirrors, and so we see changes in the interference fringes that we see at the output of the detector. So that's the basic idea of how our detector works. So from here, we move to this object here, that is essentially a prototype. This was a model. This is actually a true object. And this is an object that's very old, in 1987. It means to give you an idea of the fact that the process of building the experiment took a long time. And this is our seismic isolator. We will talk about it later after the thesis, because there is one of the demonstrators is dedicated to the pendulum. And this object is just a chain of pendulum. So essentially, that's the main idea of the super attenuator. The fact is that if you have a pendulum, you can attenuate the motion of this suspension point for frequencies that are higher than the resonance frequency of the pendulum. So if you have a very low frequency, so a very low frequency pendulum, so this means a very long pendulum, you can attenuate in a very, very wide bandwidth to above a frequency that, since it's very, if this frequency is low, it means that you have a very huge amount of attenuation, a very wide band of attenuation above this frequency of oscillation of your pendulum. This effect is increased if you put a chain of pendula. So instead of having one pendulum, you have many of them put in series. So you have the suspension point, you have a rod essentially, then you have a mass, then another rod, then another mass. And at the bottom of it, you have the object that moves the least respect to the other. And what you want to move the least, because you want what you want that is completely still, is the mirror, are the optical components of the detector. So this means that the top of the super attenuator is the part that is actually connected somehow to ground, and the seismic noise propagates one sister after the other, and at the end of this long journey that seismic noise, the ground motion makes, there is the mirror, there is the optical component, is actually the part of the isolator that is most isolated from the ground. So with this idea, that is very clever, very simple, about 12 orders of magnitude of attenuation are reached. So this is a very, very huge amount, and it's actually the main source of noise of the detector. Seismic noise is in terms of quantity, the main source of noise. And using this passive somehow solution, very simple solution, we have essentially the majority of them by many, many orders of magnitude. And in any case, we will talk a little bit more about that later. And this here we have a mirror that is, comes from the previous generation of our detector. Our detector now is in an upgrading phase. But before this upgrade, there was another upgrade that started in 2011. And this mirror comes from the previous period, the period that came before 2011. It was essentially the first phase of data acquisition of the detector. These mirrors are transparent, as you can see, so they are not the standard idea that we have of a mirror. It's not the mirror that we have in our bathroom. But simply because of the fact that these are mirrors for infrared light, so just a different frequency of light, but they are still mirror, and because they are made of pure silica. It means that the bulk, so the basic part of the mirror is still pure silica, like in a bathroom mirror. What is the most important difference is the fact, of course, that it's extremely pure silica with respect to the bathroom. And what is the difference is the coating, because in the bathroom the coating is aluminum, so it's completely opaque. This is instead transparent for visible light, but again reflective for infrared light, and is made of a very, very complex material that is the tantalum oxide. That is deposited on the surface of the mirror with a very, very complex and long process that makes actually the most performing mirrors in the world. So the best mirror in the world are used for this kind of experiment. And they are so complex that there is only one manufacturer in the world, essentially, of this mirror. It's not a company, but it's a lab that is in Lyon, in France. So there is this lab that makes the mirror for all the experiment of gravitational waves. So essentially, Virgo produced the mirror for all the experiment of gravitational waves. So for us, for LIGO, for Kagra, and so on. So that's very, very important. The nice thing that you can see also is the fact that this mirror is connected to the suspension. So you have to imagine this part here, you see this metal part, and the mirror at the bottom of the chain you have seen before, of the chain of pendula. And so this is actually the last stage, the last pendulum. And this last pendulum is made by the mirror that is connected through a series of fibers that are actually 4 fibers, 2 on the right and 2 on the left, to the upper part of the structure. So this is a cross-like structure. These two transparent wires are made of fused silica. So they are made by with the same material of the mirror, and those makes, of course, very fragile because they are like hundreds of microns, and the mirror weighs now 40 kilograms. At that time was weighing 24 kilograms. So that mirror is about 20 kilograms. And so it means each of the wire need to sustain 6 kilograms, about 6 kilograms of weight. So this makes very fragile, but this is very important because it reduces the transmission of the heat to the mirror. So this is a very important part because it reduces a lot the transmission of the heat. And another thing that you can see are the actuator, that you see these 4 coils, and that essentially induce, makes essentially a magnetic field that then produce motion of the mirror due to the fact that on the side of the mirror, on the back side of the mirror, there are attached 4 magnets. So essentially with electromagnetic induction, you can move and orient the mirror. So you see this very small cylinder, black cylinder attached to the 4 edges of this square at the center of or at the sides of the mirror. Okay, we can go outside. We will see the arm.
Valerio.
Yeah.
There were a couple of questions. I would suggest that Adriano just asks them directly to you. Is that okay? Wait before we lose connection. Don't go too far.
Okay. Now, otherwise we could
no, because it was about the attenuators, actually.
Good. Okay.
Adriano, would you like to just ask the questions?
Yes, thank you. I'm watching, and the attenuators, each one is touching the support structure. Is it locked, or is it supposed to be like that? I thought
of course. This is just a sort of exposition. It is a structure that is used to essentially to keep it stable, not stiff. Of course, in the installed device, we don't have this structure. Okay, we don't have these elements that sustain the filter. We have only the external, essentially 3. Instead of 4, we have 3 external legs that are connected to the top of the detector. So no, of course, this is not. Otherwise, we will be a short circuit to ground, of course.
The other question: why don't you use a shorter wavelength laser? Why does it have to be infrared laser?
You are right. The problem is essentially due to the mirror. So we cannot make very good mirror for different wavelengths. So the best wavelength that we can use is the infrared because of the mirror. We cannot make good mirrors for other wavelengths. And there is also another problem, is the power of the laser. If you use a powerful laser, of course, if you use a shorter wavelength, the heat that you produce will be too much. And so, of course, it will be very difficult to handle. And so at the end, using infrared is the best choice. Maybe what we will do in the future is to use slightly different wavelengths. This means still infrared, but not necessarily 1 micron. That's an idea. We use different wavelengths, little bit shorter somehow, like instead of 1 micron, 0.8 microns.
Thank you.
There is also one question regarding whether by Panagiotis. Panagiotis, would you like to ask it?
Yes, it was about the presentation of Dr. Chessa. We will be able to discover gravitational waves from a supernova because they say that the gravity is a property of space-time.
Sorry, I didn't understand the question.
If we will be able to discover any gravitational wave from a supernova.
Yeah, we hope so. But in any case, Piero also can.
We had no evidence up to now. So at the beginning, we thought that was the most likely event to be seen by our detector. We didn't know that we had so much coalescing couples in the sky. Then we discovered that that event is more likely in the sky than supernova, that being ready, seeing a supernova in the good conditions. We had no evidence now, but I'm not an expert in astronomy to make a forecast about this. Maybe Valerio knows something more than I know now, but just we know that we had no evidence of supernova at the moment.
Now the fact is that the spectrum, the other signal, that's a difficult signal to catch because it's very short, and the source should be near, has to be very near, relatively close, like tens of light years or something like this, less than 100 light years, actually close, very close. This is sorry, million. I wanted to say millions of light years, something like less than 100 million light years. Because otherwise the signal would be very easily exchanged by instrumental noise, because it's very short, it's burst-like signal, so it's not very easy, very, very short. It's like milliseconds, something like this. Instead, the signal we see are like seconds or tens of seconds, something like this, completely different kinds. But we hope, of course, that we will see them.
The 2 last years, we have saw more exploration about Betelgeuse and his oscillations in luminosity. Do we have seen something in his gravitational behavior?
What? Sorry, can you repeat that? No, sorry.
Yes, the last 2 years, Betelgeuse is a big distance.
The degree
with his luminosity oscillations. Do we have seen something about his gravitational waves or no?
No, but indeed, in that period, we were acquiring data, and we hoped that was an indication, no, of the instability of the star that then would produce actually a supernova. So that was actually, we were looking at that very closely. But at the end, you know, the star, the main constellation that then dumped. Yeah, but it's true. That was, I mean, it was the right distance to be seen from with our.
I think that in general, the larger the mass of the, for example, for the binary, the larger the mass, the greater the amplitude of the gravitational wave emitted, and the shorter the period, again, the larger the amplitude, right?
Yeah, in general, yes, approximately, yes, but there are many aspects, but yes, in general, yes. In case of a supernova, for example, there is the symmetry of the explosion is very important. No? Completely spherical symmetry of explosion would produce zero gravitational wave. So in general, if this supernova is very asymmetric, it's much better for us. But this we will see in the future. Okay, I think if there are no more questions, we will go inside the arm.
Yes, in the meanwhile, I to vote on the second part. We will probably lose connection with Valerio for a few seconds while they walk between buildings, and he will get back when he's in the tunnel. But actually, I don't know if it's only me. I get a stuck image, like, but you can.
Yeah, I see it too.
Yeah, yes. But you can see the arm, so this sort of building with the blue roof. That is actually one of the arms of the Virgo Interferometer. That is the building that hosts the tunnel. It is the tunnel that hosts the
Well, the vacuum system is operating, hosting the laser beam. And Valerio is going there. Is going to show us the vacuum system and from within the building, the blue building.
We have a hand up. Gayatri, do you want to ask a question? Please go on. I see. No. Yes.
I think Valerio is ready now.
Yeah.
Do we actually have a question or not really? No. Okay. I'm sorry.
Okay. Here now we are inside the west arm. So there are, of course, as we have seen, two arms. One is roughly aligned with north-south direction. The other one is aligned with east-west direction. This is the east-west arm. And we are here about 200 meters from the splitter. So we are, I recall you that the arm is 3 kilometers long. So we are actually close, relatively close to the splitter. And to give you an idea of the length, you see this, the lights are on, but they are not on all the tube, on all the tunnel, but only until you see there where it is dark. And this distance is about 600, less than 600 meters. And so this is giving an idea of the length of the arm. Is very, very huge. Where the beam propagates, there is always vacuum. And the vacuum that is here is extremely high. It's called ultra high vacuum. This means that it's about 10 to the minus 12 bar, so 10 to the minus 9 millibar. So you know that about 1 bar is about the atmospheric pressure. So we are 1,000, 1 billion, so 1,000 billions less respect to the atmospheric pressure. This is the pressure of all the experiment. This is very important. This makes this system, vacuum system, extremely complex because the volume of air that we have to remove is very huge. It's around 7,000 cubic meters. And this makes the biggest vacuum system in Europe. And the biggest vacuum system in the world is LIGO, simply because the arms are longer than us and longer than our arms, because are 4 kilometers and the arm here is 3 kilometers. And so this means that for the vacuum technology, those systems are the biggest challenge for this kind of technology. So this is important because vacuum has many also applications, industrial applications. So this is a very important aspect because these are the area in which the vacuum technologies push at its limits in terms of dimension of the structure. For future instruments, it will be even more complex because the length will increase in the future. And the temperature here is not controlled. So this means that it changes between the day and the night, but this does not make difference because we don't have here optical components. The light just propagates and propagates straight. Where we have optical components, we need to control the temperature very strictly, and the temperature is kept at about 21 degrees. Very, very stable. It's very, very important because otherwise the super attenuator will change its length. So this is very important. But here is not controlled. So along the tunnel is not, the temperature is not controlled. And even the noises that you can mainly hear along the tunnel, they don't have effect to the detector. So here you can make essentially the noise that you want, but you have to be extremely careful on not making noises. This means of not moving around the central area and the terminal area, means at the beginning and at the end of the arm. And the arm is made by a series of metal cylinders that are divided by a series of very stiff springs that compensate the effect of the changes between day and night of the temperature. So since the elements dilatates and compress due to the changes in temperature, we need to compensate that with very stiff springs. Essentially, of course, that are hollow. Of course, the improper inside. And the interesting thing is that the arm moves due to the fact that the ground is not very stable, due to the fact that the ground is very essentially humid. So the arm tends to float a little bit, but the important is that the fact that the optical components are instead connected to the hard part of the ground. So the optical components need to be connected to ground through using some rods that connect tens of meters below, but the tube itself can move, so can somehow float a little bit, and this floating generates changes in the height of also the order of a few centimeters. So these years, the end of the tunnel is raised by a few centimeters respect to the beginning, to the initial part of the tube. But this can be compensated, of course, due to the optics. So the optics need to be connected to the stable part of the ground, but the tube can float a little bit, and this is what happens. Okay, I don't know if there are questions on this part. By the way, outside is starting to rain, so for sure we will wait a little bit up, even though it's summer, but I don't know if there are questions.
So I have a question actually to me in the chat. How to distinguish gravitational waves and other waves in the detector? But I think maybe you will talk about this in the control room for maybe a bit longer.
Yeah, I mean, it depends on the signal. I mean, it depends on the signal. I mean, a signal that is constant. I mean, it depends on the kind of signal. For example, a signal that is like a continuous signal can be, of course, I mean, there are chances that can be exchanged for instrumental noise. No? If you have a line, something like a line, for example, at 50 Hertz, you have a line that is due to the power supply of all the devices that you have in the detector. So if you imagine on having a source of gravitational waves that has the astrophysical characteristics, should be a pulsar, not a black hole or a neutron star, should be a pulsar. So it's a neutron star that is spinning. Imagine that it emits exactly at that frequency. In that case, you will be masked by instrumental noise because it will be a line exactly at the same frequency. For the other signal, it's essentially impossible to essentially exchange one for the other because the signal of the gravitational wave has a very specific shape that you can compare with the signal of your detector. So you can make a statistical analysis of this comparison. And if this statistical analysis gives you a huge significance, this means that you are seeing a signal, and the significance that we have for many signals is really enormous. So, for example, there is a number that is called FAR, false alarm rate. This number gives you the time that you need to wait until you see essentially a signal that is not a gravitational wave, that is exactly the one like you have seen. So imagine that the signal is not a gravitational wave, but it's just a statistical fluctuation, just noise. how long you need to wait to see this kind of signal, how many years of data. This means billions of years of data. So there are signals that are, the probability is like 1 over the few billions of years of data. So this gives you an idea of how is unlikely to exchange a signal of a gravitational wave for spurious noise. For several signals, is extremely low. Of course, it depends on the signal to noise ratio. If you have a signal that is very weak because it's very far, the source is very far from here, this means, of course, you will have a false alarm rate that is lower. But still, we speak about all orders of hundreds or thousands of years. So this gives you an idea of the statistical significance of the detection that we make. So essentially, the answer is no, it's almost impossible to exchange the gravitational waves for experimental noise, to change them, but could be possible instead when we will see continuous sources, because those are very tricky. And also for bursts, like the supernovae, their sources are very tricky because they're very short. So those kind of signals. But for binary black hole, binary neutron star is extremely, very unlikely. It's essentially impossible.
And Valerio, before you leave again, can you repeat how long the tunnel is?
3 kilometers, of course, it's 3 kilometers. But the part that you see the light on right now is about 600 meters. So it's just then you see dark, but instead, of course, the tube continues.
Thank you.
Okay. So we will now go outside. We hope that we will not take the rain. We will not get wet, and then we will go inside the experimental area.
Valerio, we do have a question actually by Stella.
Okay. Okay, let's do before exiting.
Stay there. So she asks, basically, she said, so you compare the signal with the other detectors before you come to a conclusion from where it comes from. Basically, yes, I would say.
Yeah, I mean, we use the signal from our detector, to triangulate the origin of the position in the sky, to obtain the position in the sky of the source. I mean, alone, LIGO alone or Virgo alone cannot localize the source. So this is, this means that we cannot make we can make astronomy only in the moment in which we can localize an area in the sky in which is the origin of the gravitational waves. And so this is very important. Indeed, the gravitational wave astronomy started when we saw the first signals of for example, binary neutron star, because in that area we saw also a star. Only if we localize the area we can do. So this is very important. Study gravitational waves without knowing the origin would be useless. But however, if you use only one instrument or only 2 instruments, the localization is extremely bad. So it's like not to know, essentially the angle is so big, the area is so big that you don't know where the origin of the signal. Okay.
Thank you. Sorry, Stella, I didn't quite understand. She says, so that...
May I ask? Cannot be out of work when you update a detector, so much must work at least 2 of them, if I understand.
When we upgrade the detector, we upgrade all the detectors together. So, for example, now we are upgrading the Virgo. Virgo is upgrading, but also LIGO is upgrading. Because again, we cannot imagine that, for example, we finish if we start acquiring data, but we are alone. So indeed, we need to start together, to stop together and to start together. So this is a very important fact. We need to collaborate with LIGO in order to be synchronized in the planning. This is very important. So for now, for example, now we are upgrading and LIGO is upgrading. And until we have finished, or until LIGO has finished, we cannot start acquiring gravitational waves. This could change in the future when there will be more instruments. If we will have, for example, instrument in Japan that is now being built, that is starting to work, but not very good. When we will have a good instrument, good performing instrument, we could think of having, for example, since we have in that case 4 instruments, we can think of upgrading 1 instrument, keeping the other 3 on, and this we can rotate that. So that could be also a strategy. But for now, since we have only 3 sensitive instruments to see gravitational wave, we can only start and stop together the runs. There are no other choices.
May I suggest that Valerio goes to the central building and Piero can answer the further questions, because otherwise we very late.
Okay.
I try.
Yeah, Piero. So the Gayatri is asking why you need 3 kilometers. Can you maybe repeat?
Yeah. If you remember, I showed you a figure which is the relative change of length due to the gravitational wave, the amplitude we expect from astronomical events, and that number was 10 to minus 21. So we have to multiply this number by a long length. So we have when you do this, you can go into some band of detection where you can have the wanted sensitivity. If you are shorter arms, then you have smaller signals, and you have to add even a better attenuation. You need more attenuation of noise, and you can go up to that to that sensitivity, that attenuation with the short arms. In Germany, we have a shorter interferometer, and had no results at the moment like we had. And indeed, the only Michelson scheme is not enough again. So we had to improve the system by adding mirrors at the beginning of the arms to multiply the number of travels of light up and down along the arms. So now we had this length multiplied by a factor due to the finesse of the Fabry-Perot cavities on arms, and this multiplication gives us a higher sensitivity to the signal. So you have to have a long theoretical length. Maybe you can imagine to have shorter arms with higher finesse Fabry-Perot. I'm not an expert in this. I don't know at what point you can reduce the length, but the research does not go in that direction. We are going to think to longer arms with good cavities to amplify again more the number of travels of light up and down. And so next interferometers will be built with higher lengths, up to 10 kilometers. I hope this answers.
Yes.
Yes. So Adrian asks about those in Japan and India. Adriano, do you mean about the length?
The length of yes. them will be 10 kilometers?
No, I was thinking to a new generation detectors. We are thinking to the design now. They are not implemented, not even, we have no executive design at the moment. I can tell you what Valerio is, which he knows a lot of information more than me, can be precise about the length of Kagra and LIGO India. But I was not speaking about those two. Oh, I was thinking about the next generation.
About the Einstein telescope.
Yeah, exactly.
I have a question about that. So the Einstein telescope is supposed to be 3 interferometers, you know, located in a sort of a triangle together.
Yeah, yeah. It has been the update. The design of the Einstein telescope is a triangle. Yeah, with 2 interferometers. That means it is made by 2 Michelson interferometers with one arm, common arm, a shared arm, and the 2 other arms goes to touch on the other vertex. There are 2. It is intended to be worked with 2 different wavelengths, and we renounce to perpendicularity of arms to have a single station at the end of the to control 2 end mirrors at the same time. So we leave the perpendicularity of arms. We go to a triangular shape to have a point where we can drive 2 end mirrors by 2 different interferometers, and we add we plan to have 2 beam splitters in the other 2 vertexes.
Next question is LISA still a long time away? It is, right? But LISA?
Yeah.
Interferometry space antenna.
If it's
The next
a long time
step
away, I think.
On detecting gravity waves, gravitational waves.
I don't know about LISA.
Manolis, do you remember? I think
that that LISA is supposed to launch sometime in 10 to 15 years from now.
Yeah, 10 is what I kind of had in mind, but
also take into account that LISA will be sensitive in a different frequency range than Virgo, LIGO, right?
yes, it would be complementary. They will go to lower frequencies, longer arms, no background noise, no seismic noise. So they will look at somewhat different sources as well.
Mm-hmm.
It will be very interesting.
Yes. Actually, the arms of LISA are expected to be some million kilometers long, which means that.
Am I wrong? 2.5 million?
2.5, I think. And the thing is that maybe this way they will be able to detect also compact binaries from within the galaxy.
Let's hope so. We completely lost Valerio. Am I wrong?
No. But one thing that is very interesting about LISA is that they may be able to detect the gravitational wave background. Similarly to CMB, there is the so-called gravitational wave background, which is stochastic noise, let's say. Maybe LISA will be able to detect that. Let's see what happens. I think that there might be a connection error.
No, I think we're going back.
Okay.
So I think Valerio is coming back. Yeah, primordial gravitational waves.
Yes.
It's the background really much like the CMB, the cosmic microwave background, which is light. But the interesting, there are many interesting things. But the interesting thing is that it dates back from the beginning, because the universe was not opaque to gravitational waves as it was to light. So it would actually be a much earlier time. Somebody corrects me if I say nonsense, huh? But primordial gravitational waves will come from a much earlier time that the cosmic microwave background. And so we will be able to see farther in the beginning of the universe, let's say. I hope.
Yeah.
Valerio should be back.
Okay, yeah, sorry, it takes more than usual. So it was raining. And okay, here we are inside the experimental area. So you will see now a series of vacuum envelopes that contain the superatomic. So you're seeing this huge tower in the other building. This huge tower is not naked somehow, it's covered through a series of envelopes, of metal envelopes. They can use, of course, an vacuum inside. And at the bottom of each of these long towers, there is a mirror. Instead, at the bottom of the short tower, there are benches. So the bench, so the short tower we have in front of us now is the detection bench. So we start from the outside, we start from the end of the detection. This is the detection suspension. The short tower, like the one that is much shorter. At the bottom of that is a bench with a seat of photodiode. So this part here is exactly like the plastic sheet that gets into the model. But instead of having simply a plain light projector, we have a series of sensors. Photodiodes are essentially like eyes, but they are not, of course, like our eyes. They're much more sensitive, and they can also measure infrared light, so different bandwidth respect of our eye. And from that signal that we use, that we obtain from the photodiodes, we detect gravitational waves. So from that signal, once this signal is processed, we can obtain the gravitational wave sequence. What are the other towers? The other towers are the other optical components. In particular, are the components of the Michelson interferometer. So we have the laser, but you cannot see it because essentially it's on the left side. So it's covered right now by this. You see this wall you see on the left. You see on the first suspension that you see on the left is called power reflector. The suspension that is made by semi-reflective mirror that allows you to cover the light that goes essentially towards the laser. Okay, so it's a recycling. When you recycle, you see that you press away, but you recycle them. We do the same with the light. The light that go to the laser is put back in it. The tower that you have on the right set the distance. So it's why it's like the cube and so at the bottom of the tower is divided into the right. 50% goes on the right. So passes through. You see that on the right there is a tower. That tower at the bottom of that tower is a glass. So essentially glass. It's a very transparent mirror, not completely transparent, a little bit reflective, almost completely transparent. That makes the light enter. Yeah. So on the right you have the north arm. So on the right, north arm starts, and you have 3 kilometers.
Valerio,
yeah.
I'm sorry. There is some noise behind the I don't know, some reverberation. Maybe yeah.
I don't know. Now it's better or
Secondo me la
maybe...
pioggia. Secondo me la pioggia.
Yeah, there is also it's raining, by the way. So it could be that.
Better, thank you.
Yeah, yeah. So it maybe yeah, or the position of my headphone, but by the way, it's raining, so it could be that the noise of the rain. And in any case, on the right there is the North Arm, and on the front, in front, instead of the split there is that where West Arm starts. So again, there is another tower, and at the bottom of that tower there is another mirror that is the input mirror of the West cavity. So the tower on the right of the splitter is the input mirror of the North cavity. The tower in front of the splitter is the input mirror of the West cavity. And those mirrors are extremely important. They are important like the mirrors that are at the end of the arms. Why? Because due to that, we can increase the optical length of the detector by a factor that is about 400. This means that the light does not make only a round trip inside the arm, but makes 440 reflections. This is a very, very huge difference in length, because of course, instead of having 3 kilometers, you have 1,300 kilometers that are made by the light. So it is a very important factor. And we obtain that by using those two essentially almost completely reflective, almost completely transmitting beam, but slightly reflective. So they let light enter, but they reflect them when it comes back from the end mirror a little bit. So the light, again, comes back at the bit splitter after this 1,300 kilometers of journey on one arm and on the other arm, passes through the bit splitter, then passes through this long tower. You see, there is a long tower in front of the detection. This is called the senior recycling. That essentially is like the lens that we have in our small model. Then this sort of lens focalized on the detection bench where we obtain the gravitational wave. We obtain the signal in which the gravitational waves are contained. And so the noises that you are hearing, there are due to many things. One could be also rain, but there is also a background due to the pumping system of the vacuum. So the vacuum continuously is on, the system is continuously on, so makes sort of background noise due to the fact that it's always active. So, and you can see also the sign there, this is blinking, because of course the light of the laser is on. And this is dangerous. I mean, since it's visible, it's not visible, the laser, but still is, even if it is infrared, is still powerful enough to damage our eye, because it's very, very powerful, of the order of tens of watts. So it's very, very powerful for a laser. Of course, not for a lamp, but it is for a laser. And so it can easily damage our eye, even though it's infrared. And okay, I don't know if there are questions. Of course, here inside there is a lot of stuff, a lot of things to discover somehow. But this is just was a brief overview of what is inside this video. Okay, I don't know, Julia, Manolis.
Yes,
I'm
yes.
looking, but I don't think.
Can I ask something while we are waiting? Okay, so the vacuum inside, let's say, these towers, why is it important? What type of noise does it help us eliminate?
Essentially, the main problem, if we will not eliminate air, will be the changes in the refractive index of the air. So the fact that the pressure changes between, for example, a good or bad day, for example, today, even though we are in summer, it's raining, and so the pressure decreased respect to yesterday. This would have caused a change in the refractive index of the air, and that will make essentially changes that maybe will not allow to see gravitational waves, for example. But of course, there are also other effects, because inside there is also humidity. This humidity can go on the mirror themselves, so they will become they will make some, like some small raindrops, like a small fog on on the surface of the mirror. So there are many negative effects due to the humidity and due to many things that can be inside air. Also, in air can be also polluting agents. For example, the fact that we are close to a city, not very big, but still a city. And so there is, of course, there are the cars that produce smog, that produce gases. And those gases are inside there, also here. Those gases can damage, in the long term, of course, can damage the surface of the mirror. So there are many things that are negative in keeping the air. And regarding the suspension, because of course for the mirror, those are all the reasons I told you. Essentially, the beam is disturbed and also the surface of the mirror. But for the suspension, the main advantage of having vacuum is the fact that everything is more stable. Because if there is air, there is this continuously sort of flux of currents of air, fluxes of air inside, and it will move the suspension. So everything is much more stable, much more still from the mechanics. I'm talking only about the mechanics point of view if you don't have air. So this means, for example, that the resonances of your pendula are much more, the quality factor of them is much more higher. This means they're very much more narrow in frequency, the single resonant frequency of your pen. So this is very important. So there are tons of reasons why it's important to remove air.
When we did the virtual visits with students, many students who were confused and they were saying that the vacuum is important for seismic isolation. Would that be right?
Yeah, it is, but in an indirect way, due to the fact that the suspension works a lot better, so it isolates much better if there are no air. So that's essentially it. Because the mechanics behaves differently if you have air or if you don't have.
Okay, thank you. Are there other questions? Okay, I think that we don't have any other questions right now.
Okay. So I think for now, I think we can close the visit here and then make a break if you agree, as we have foreseen. Maybe a shorter break than we thought at the beginning, and then we will restart with the session. Is it okay for you?
Yes, I think that's okay. I believe that we will leave the link open so people can choose to just stay on. You just switch off camera and mic and everything, and we reconvene at 12.
Okay.
Okay, very good.
Thank you, Valerio. Thank you.
See you later. See you in half an hour. Bye.
Thank you.
Thank you.
Bye.
Thank you.
Bye.
Bye.
Bye.